Chicago, 1910. Steam rises from manholes as construction crews install the first high-rise plumbing systems designed to last a century. The engineering wisdom flowing from Eastern firms was clear. Use thin wall copper where possible. Keep costs down. Follow European efficiency models. American plumbers were installing something completely different. Thick wall copper tubes with walls nearly twice as heavy as standard practice. Water velocities deliberately slowed to under 8 feet per second in cold lines, under 5 feet per second in hot water circulation. Installation methods that prioritized craftsmanship over speed. Every joint reamed and deburred by hand. Every bend carefully swept to reduce turbulence. The Eastern contractors called it wasteful American excess. The budget managers calculated the copper premium and shook their heads. But in basement pump rooms across the Midwest, a new doctrine was taking shape, one that would prove thin wall efficiency wrong in the most definitive way possible. Over 100 years later, those same thick copper lines are still delivering clean water to Chicago buildings, while modern plastic systems designed to last decades are failing in 20 years or less. The difference wasn't just in the metal, it was in understanding what water does to pipes when nobody's watching. The Michigan Avenue skyline stretched upward in 1910 like a declaration of American ambition, each new floor demanding innovations that European engineering manuals had never contemplated. In basement mechanical rooms across Chicago's rising commercial district, a quiet revolution was taking shape around specifications that defied every cost-cutting principle the Eastern construction firms had imported from across the Atlantic. Thomas McKenna ran his caliper along a section of 3/4-inch Type K copper tubing, the metal clicking softly as he measured the wall thickness at 65 thousandths of an inch. Around him, stacks of copper pipe gleamed under electric work lights, each piece representing a bet against conventional wisdom that said thin wall construction was the path to profitable plumbing. The Eastern firms were installing Type M at 32 thousandths, sometimes 28 thousandths in smaller sizes, chasing every penny of material savings they could squeeze from their specifications. Copper's heavy and expensive, the budget managers kept telling him, their ledger sheets filled with calculations that reduced building systems to simple arithmetic. Why not follow the New York model with thinner walls? The pressure ratings work out the same on paper. McKenna had heard this argument through 3 major projects, and each time he responded with the same methodical demonstration. He would lay 2 pipe samples side by side, pointing to the mass difference that his calipers revealed in precise measurements. Type K carried nearly twice the copper as Type M in the same diameter, and that extra metal wasn't decoration. It was insurance against every force that turned reliable plumbing into emergency repairs. The chemistry behind his conviction was as solid as the copper itself. ACC 12200 copper delivered 99.9% purity with phosphorus content held between 15 and 40 thousandths of a percent. The phosphorus acted as a deoxidizer, removing trapped oxygen that created weak points in the crystal structure. Every piece that entered his mechanical rooms had been processed to eliminate the hydrogen embrittlement that plagued cheaper alternatives. But chemistry alone wouldn't win the argument. The real proof lived in the hydraulics tables that McKenna kept posted above every pump station like safety regulations. Water velocity in cold lines never exceeded 8 feet per second. Hot water circulation stayed under 5 feet per second without exception. These weren't suggestions pulled from manufacturer recommendations. They were hard limits backed by decades of European experience with erosion corrosion in high-velocity systems. The velocity doctrine separated American building practices from everything the Eastern firms had learned from British and German engineering traditions. European systems accepted higher flow rates as necessary compromises, trading long-term durability for immediate hydraulic performance. McKenna's approach inverted that calculation entirely. Every pump was sized to move the required volume at speeds that let protective films form and persist inside the copper tubes. The film formation process fascinated McKenna in ways that his crew found both admirable and slightly obsessive. When copper contacted treated water under controlled flow conditions, a thin layer of cuprous oxide developed along the interior surface. This microscopic coating acted as a barrier between the metal and potentially corrosive elements in the water supply, but the film only survived when flow turbulence stayed within limits that prevented mechanical abrasion. Think of it like painting a fence in a windstorm, McKenna explained to his foreman during their weekly technical meetings. The paint might be perfect, but if the wind keeps hitting it before it dries, you'll never get coverage that lasts. Same principle with the oxide layer. High velocity is like sandblasting that protective film off the inside of every pipe. The mathematics of his system filled notebooks that McKenna kept locked in his office desk. The 12-story residential building they were completing required 12 vertical risers spanning 16 floors each, translating to approximately 2,400 linear feet of 3/4-inch to 2-inch copper tubing. 700 individual sweat joints connected the network, each one requiring proper flux application, temperature control, and post-installation cleaning to prevent residual chemicals from attacking the copper later. Installation sequences followed protocols that McKenna had developed through trial and expensive error on previous projects. Every cut received careful reaming and deburring to eliminate sharp edges that created turbulence points. Joints incorporated sweeping turns rather than sharp elbows, wherever space permitted. Union connections appeared at strategic maintenance access points, allowing future repairs without cutting into permanently installed sections. The commissioning process would test every assumption built into McKenna's specifications. 24 hours of pressure holding at 125 pounds per square inch would reveal any joint failures before the system carried live loads. Staged temperature cycling up to 140 degrees Fahrenheit would stress the expansion characteristics of the copper network under full operating conditions. Budget meetings continued to challenge every aspect of McKenna's methodology. The thin wall advocates presented cost analyses that made compelling arguments for following established Eastern practices. Type M copper delivered identical pressure ratings at significantly lower material costs. Installation labor remained essentially unchanged regardless of wall thickness. The mathematics of immediate savings versus long-term performance created spreadsheet battles that McKenna usually lost in front of building owners focused on construction budgets rather than life cycle costs. Yet McKenna persisted with the quiet confidence of someone who had seen both approaches tested by time and Chicago water chemistry. Thin wall copper might meet code requirements and pass initial pressure tests, but meeting minimum standards had never been the goal of American building practices that aim to last generations rather than decades. The extra copper mass in Type K construction bought time against every corrosive force that building owners never considered until emergency repairs disrupted their operations. The real test would come not in commissioning reports or budget presentations, but in mechanical rooms 15 or 20 years hence, when building superintendents would either appreciate the foresight of heavy-gauge construction or curse the penny-wise decisions that left them replacing failed piping systems while tenants demanded uninterrupted service. The ASTM B88 standard arrived at McKenna's project office in 1911 as a 40-page technical document that would reshape American plumbing specifications for the next century. Unlike the informal guidelines that had governed copper installation since the 1880s, this standard codified wall thicknesses, pressure ratings, and installation practices into a systematic doctrine that separated engineering fact from trade mythology. McKenna spread the specification sheets across his drafting table, studying the tabulated data that confirmed his instincts about thick wall construction. Type K copper tubing carried working pressure ratings that provided substantial safety margins above typical residential conditions. 3/4-inch Type K rated for 440 pounds per square inch at room temperature, dropping to 330 pounds per square inch at 200 degrees Fahrenheit. Even accounting for thermal derating, the specifications offered massive headroom above the 48 to 80 pounds per square inch that Chicago buildings typically demanded. The pressure ratings told only half the story. Wall thickness controlled hoop stress, the circumferential tension that pressure created around the pipe's interior circumference. Thicker walls distributed this stress across more copper mass, reducing the peak strain that led to fatigue failures over decades of pressure cycling. McKenna calculated that Type K construction reduced hoop stress by nearly 40% compared to Type M alternatives. a difference that accumulated into reliability advantages that wouldn't appear on commissioning reports, but would determine whether pipes lasted 30 years or 70 years. The mechanical properties of C12-200 copper provided the foundation for everything McKenna was building. Tensile strength of 30,000 to 37,000 pounds per square inch gave the material enough ductility to handle thermal expansion without cracking. Yield strength around 10,000 pounds per square inch meant the copper would deform elastically under normal operating stresses, returning to its original shape when loads decreased. The phosphorus content that McKenna measured so carefully acted as both deoxidizer and grain refiner, creating a microstructure that resisted corrosion initiation at crystal boundaries. But even as McKenna refined his copper specifications, reports from construction sites across America described a new challenge to traditional metal plumbing that wouldn't reach Chicago for another 40 years. Experimental installations of cross-linked polyethylene tubing, known as PEX, were being tested in European radiant heating systems with performance claims that seemed to promise the advantages of metal without the installation complexity. The early PEX specifications that McKenna reviewed in trade journals listed impressive pressure ratings: 160 pounds per square inch at 73 degrees Fahrenheit, 100 pounds per square inch at 180 degrees Fahrenheit. The material appeared to offer installation flexibility that copper couldn't match, bending around obstacles without joints, connecting through crimped fittings that eliminated soldering operations entirely. McKenna studied the polymer chemistry with the same methodical approach he applied to copper metallurgy. Cross-linked polyethylene achieved its strength through chemical bonds that connected individual polymer chains into a three-dimensional network. The cross-linking process created molecular bridges that prevented the material from melting under normal operating temperatures, giving PEX thermal stability that standard polyethylene lacked entirely. Yet the pressure ratings that looked so impressive on specification sheets represented only one dimension of material performance. McKenna noted that PEX manufacturers qualified their pressure ratings with extensive footnotes about temperature derating, chemical compatibility, and service life calculations. The ASTM F20023 standard that governed PEX evaluation subjected samples to hot water containing 4.3 parts per million free chlorine under continuous flow conditions, deliberately creating aggressive oxidation conditions that modeled decades of service in chlorinated water systems. Municipal water treatment practices across America routinely maintained residual chlorine levels up to 4.0 milligrams per liter, the maximum residual disinfectant level that EPA regulations permitted in public water supplies. The chlorine that protected public health by preventing bacterial growth also created chemical stress that aged polymer materials through oxidation reactions that consumed antioxidant additives over time. The chlorine resistance categories that PEX manufacturers encoded into their material designations revealed the complexity behind simple pressure ratings. Category 1 indicated basic chlorine resistance suitable for cold water applications. Category 3 provided enhanced chlorine resistance for mixed temperature service. Category 5 represented the highest chlorine resistance available for continuous hot water circulation. Each category corresponded to different antioxidant packages and cross-linking chemistries that affected both performance and cost. McKenna recognized that the numeric codes told only part of the polymer story. The second digit in PEX material designations indicated ultraviolet light resistance, with Category 1 allowing 30 days of direct sunlight exposure before installation, Category 2 extending that limit to 90 days. Construction schedules that left PEX exposed during framing operations could compromise material properties before the system ever carried water, creating premature aging that wouldn't manifest as failures until years after installation. The fundamental difference between copper and polymer approaches to plumbing emerged from their respective responses to operating stresses. Copper systems relied on protective oxide films that formed naturally when flow velocities stayed within limits that prevented mechanical abrasion. PEX systems depended on antioxidant chemicals that prevented polymer degradation, but depleted over time through reactions with chlorine and dissolved oxygen. McKenna's velocity tables took on new significance when viewed alongside polymer degradation mechanisms. The 8 foot per second limit for cold water and 5 foot per second limit for hot water that protected copper's oxide layer also minimized mechanical stress on polymer materials. But where copper could tolerate occasional velocity excursions without permanent damage, polymers accumulated degradation that advanced irreversibly from molecular chain scission through antioxidant depletion toward eventual brittleness and failure. The laboratory testing that supported both copper and PEX specifications created artificial conditions that compressed decades of service into months of accelerated aging. Copper samples showed predictable behavior under thermal cycling and pressure stress, with failures occurring through well-understood mechanisms like fatigue crack propagation or localized corrosion. PEX testing revealed more complex failure modes tied to antioxidant chemistry and molecular structure, changes that varied with temperature, chlorine concentration, and dissolved oxygen levels. McKenna filed the PEX technical literature alongside his copper specifications, recognizing that both materials would eventually compete for the same applications in American buildings. The polymer advantages of flexibility and installation simplicity appealed to contractors facing labor shortages and schedule pressures. But the long-term performance questions surrounding chlorine resistance and antioxidant depletion suggested that material selection would ultimately depend on whether building owners prioritized initial cost savings or life cycle reliability in their mechanical system investments. The fabrication shop that McKenna established in the basement of his Michigan Avenue project operated with the precision of a watchmaking facility, each copper joint receiving individual attention that mass production methods couldn't duplicate. By 1912, his crew had developed assembly sequences that eliminated the random quality variations that plagued conventional plumbing installations across Chicago's construction sites. Every section of copper tubing arrived at McKenna's shop pre-cut to exact dimensions, with allowances calculated for thermal expansion under full operating temperature. The cutting operation used rotary tube cutters that produced clean, square ends without the crushing deformation that hacksaw cuts created. Each cut received immediate reaming with tapered tools that removed internal burrs while preserving the tube's interior diameter. The deburring process eliminated sharp edges that created turbulence points where erosion corrosion initiated during decades of service. McKenna's fabrication doctrine required sweeping bends wherever space constraints permitted, using bend radii that minimized pressure losses and turbulence generation. Sharp 90-degree elbows appeared only where architectural limitations made sweeping turns impossible, and even these received careful orientation to ensure that high-velocity flow impacted the fittings back rather than creating swirl patterns that abraded protective oxide films. The soldering operations that connected McKenna's prefabricated sections followed temperature protocols that his crew measured with pyrometric crayons marked for specific melting points. 50-50 lead tin solder flowed at temperatures between 370 and 420 degrees Fahrenheit, providing a working range that prevented overheating damage to the copper while ensuring complete joint penetration. Flux application preceded every joint, with acid-based cleaners that removed oxide films to promote solder adhesion, followed by immediate post-soldering cleaning that eliminated flux residues before they could initiate long-term corrosion. The riser installations that began in earnest during 1913 showcased McKenna's systematic approach to vertical plumbing distribution. Each riser followed identical routing through mechanical chases, designed specifically for plumbing access, with horizontal branch connections spaced at precise intervals that balanced hydraulic performance against construction complexity. Union joints appeared at strategic locations where future maintenance might require system disassembly, eliminating the need to cut permanently soldered sections during repair operations. McKenna's pump room installations embodied his velocity discipline through equipment sizing that prioritized flow control over raw hydraulic capacity. Centrifugal pumps operated at speeds that delivered required flow volumes while maintaining circulation velocities under 5 feet per second in hot water loops. The pump curves that McKenna posted throughout his mechanical spaces showed operating points selected for efficiency and longevity rather than maximum performance, with safety margins that prevented cavitation damage during peak demand periods. The recirculation loops that McKenna designed for hot water distribution represented his most sophisticated application of flow dynamics principles. Unlike conventional systems that sized pumps for rapid temperature delivery, McKenna's approach maintained continuous circulation at velocities that preserved protective oxide films while ensuring hot water availability at fixtures. Temperature maintenance required pump operation around the clock, but the energy costs were offset by reduced heat losses through properly insulated distribution piping. The hydraulic calculations that governed McKenna's system design filled engineering notebooks with friction loss tables, expansion calculations, and pressure drop analyses that accounted for every fitting and elevation change in the distribution network. Hayes and Williams' friction coefficients for new copper tubing started at 130, decreasing gradually as protective oxide films formed and matured. McKenna's designs assumed coefficient values of 120 for long-term calculations, providing conservative margins that ensured adequate pressure delivery throughout the system's service life. The commissioning procedures that McKenna developed for his completed installations subjected every component to stress testing that exceeded normal operating conditions. Initial pressure tests held the entire system at 125 pounds per square inch for 24 consecutive hours, revealing any joint failures or material defects before the system entered service. Temperature cycling followed pressure testing, with hot water circulation gradually increased from ambient temperature to 140 degrees Fahrenheit while monitoring for leaks, pressure variations, or unusual noises that indicated flow problems. McKenna's quality control extended beyond installation procedures to encompass material verification that few contractors considered necessary. Random sampling of copper tubing confirmed wall thickness measurements against ASTM B88 specifications, ensuring that Type K material actually delivered the 65 thousandths wall thickness that his calculations assumed. Solder composition testing verified tin-lead ratios that affected joint strength and corrosion resistance. Even flux chemistry received analysis to confirm acid content that balanced cleaning effectiveness against post-installation corrosion risks. The building superintendent, who would inherit McKenna's completed system, received training that transformed routine maintenance into systematic preservation of design performance. Pump operation logs tracked flow rates, pressure differentials, and temperature patterns that indicated system health. Valve operation schedules prevented stagnation in unused branches while maintaining circulation patterns that supported oxide film stability. Water quality monitoring detected changes in chlorine residuals, pH, or dissolved oxygen that could affect corrosion rates in the copper distribution network. McKenna's documentation protocols created maintenance records that would guide system operation for decades beyond his direct involvement. Every major component carried identification tags with installation dates, manufacturer specifications, and performance parameters. Piping drawings showed not just routing and connection details, but also design velocities, pressure ratings, and expansion allowances that future maintenance crews would need for proper system modification. The cost accounting that tracked McKenna's methodology revealed initial expenses that exceeded conventional plumbing installations by approximately 15%. The premium reflected heavier copper gauges, more complex fabrication procedures, and installation labor that prioritized precision over speed. But McKenna's calculations projected maintenance savings and extended service life that would recover the initial investment within 12 years, with subsequent decades of operation delivering substantial economic advantages compared to thin-wall alternatives. The performance monitoring that began with system commissioning would continue throughout McKenna's career, providing data that validated or challenged every assumption built into his design methodology. Flow measurements confirmed that velocity limits preserved protective films and prevented erosion damage. Pressure testing revealed whether heavy-gauge copper actually delivered the fatigue resistance that hoop stress calculations predicted. Temperature cycling demonstrated whether thermal expansion allowances prevented stress concentrations that caused premature failures. By 1915, McKenna's approach to copper plumbing had evolved from individual project methodology into systematic doctrine that could be replicated across different building types and operating conditions. The principles that governed his work, velocity control, material specification, and installation precision, represented American engineering philosophy that valued long-term performance over short-term cost optimization. The Palmolive building project that began construction 3 blocks from McKenna's completed Michigan Avenue installation in 1916 represented everything his methodology opposed. The general contractor, pressed by aggressive completion schedules and razor-thin profit margins, awarded the plumbing contract to a firm that promised 30% cost savings through thin-wall copper and accelerated circulation velocities that would deliver hot water faster to upper floors. McKenna watched the competing installation from his office window as crews installed Type M copper with wall thicknesses averaging 32 thousandths of an inch in 3/4-inch lines, nearly half the mass of his Type K specifications. The circulation pumps that the contractor specified operated at speeds that pushed hot water through the distribution system, at velocities exceeding 12 feet per second, well above the 5-foot limit that McKenna's experience had established as the threshold for protective film stability. The cost advantages of the thin wall approach appeared immediately in material procurement and installation labor. Type M copper reduced raw material expenses by approximately 25% compared to Type K alternatives, while the lighter weight simplified handling and reduced installation time. The high-velocity circulation promised rapid hot water delivery that building tenants would appreciate, eliminating the wait times that conventional systems created during peak demand periods. Yet McKenna recognized warning signs in the installation practices that the competing project employed. Pipe cutting operations used reciprocating saws that created rough, uneven edges requiring minimal deburring before soldering. Joint preparation eliminated the careful flux cleaning and temperature control that McKenna's crews practiced, with salter application proceeding at whatever pace the installation schedule demanded. The sweeping bends that McKenna insisted upon gave way to sharp elbows installed wherever they simplified routing through congested mechanical chases. The system commissioning that occurred in late 1917 revealed performance characteristics that initially vindicated the thin wall approach. Pressure testing confirmed that Type M copper met code requirements for residential service, with no joint failures or material defects detected during initial operation. Hot water circulation delivered temperature rises at fixtures within seconds of valve operation, satisfying building tenants who had experienced delays with conventional systems. Operating costs remained within projected parameters, with pump energy consumption offset by reduced heat losses through the accelerated distribution network. McKenna's concerns about long-term performance found no immediate validation in the competing system's early operation. The thin-wall copper showed no visible signs of degradation during the first 3 years of service, maintaining pressure integrity and temperature delivery performance that satisfied both building management and tenant expectations. The cost savings that the contractor had promised materialized as projected, delivering immediate financial advantages that made McKenna's heavy-gauge methodology appear unnecessarily conservative. The first indication of problems emerged in 1921, when building maintenance personnel reported intermittent pressure fluctuations in hot water lines serving upper floors. Investigation revealed pinhole leaks in Type M copper sections located at sharp elbows, where high-velocity flow created turbulent conditions that abraded protective oxide films. The leaks appeared as tiny perforations that allowed water seepage without catastrophic failure, creating moisture problems in wall cavities that required extensive drywall replacement. Microscopic analysis of the failed copper sections revealed erosion patterns that confirmed McKenna's predictions about velocity-induced corrosion. The interior surfaces showed characteristic gouging where turbulent flow had mechanically removed protective films, exposing fresh copper to aggressive attack by dissolved oxygen and residual chlorine in the building's water supply. The thin wall thickness that had provided initial cost savings offered insufficient copper mass to resist the gradual material loss that high-velocity operation created. The repair operations that began in 1922 required extensive demolition to access failed piping sections embedded in finished construction. Each pinhole leak demanded cutting out affected tube sections and installing new joints, with associated restoration of wall finishes, insulation, and decorative elements. The building's insurance carrier documented repair costs that exceeded the original installation savings within the first 5 years of operation, with additional failures anticipated as the erosion process continued. McKenna's analysis of the failure patterns confirmed his theoretical understanding of copper corrosion mechanisms under high-velocity conditions. The protective cuprous oxide films that form naturally in properly designed systems required flow velocities under 5 feet per second to remain mechanically stable. Higher velocities created shear stresses that stripped away protective layers faster than they could regenerate, leaving bare copper exposed to electrochemical attack that gradually consumed pipe wall thickness. The economic impact of the premature failures extended beyond immediate repair costs to encompass business interruption, tenant relations, and long-term building value degradation. Water damage from pinhole leaks required emergency shutdowns that disrupted normal building operations, with tenant complaints and potential lease disputes over habitability issues. Property managers faced the prospect of comprehensive plumbing system replacement decades earlier than conventional maintenance planning anticipated. But the thin-wall copper failures represented only the beginning of material challenges that would confront American building systems in subsequent decades. By 1950, experimental installations of cross-linked polyethylene tubing were beginning to appear in residential construction, promising installation advantages and material cost savings that made even thin-wall copper seem expensive. The early PEX installations that McKenna observed in tract housing developments offered compelling advantages over traditional copper systems. The flexible tubing eliminated joints in concealed locations, reducing potential leak points to connection fittings at fixtures and equipment. Installation procedures required no soldering operations, with crimped mechanical connections that plumbers could complete using portable tools without open flames or temperature control concerns. Yet McKenna noted that PEX manufacturers qualified their material warranties with extensive limitations regarding water temperature, chlorine concentration, and ultraviolet light exposure during construction. The polymer chemistry that provided PEX flexibility also created vulnerabilities to chemical degradation that copper systems didn't experience. Antioxidant additives that protected the cross-linked polyethylene from thermal and chemical aging would deplete over time, advancing the material through predictable stages from ductile performance toward eventual brittleness and failure. The chlorine resistance categories that PEX specifications encoded into material designations revealed the complexity behind apparent simplicity. Category 1. PEX provided basic chlorine resistance suitable for cold water applications, while Category 3 and Category 5 materials incorporated enhanced antioxidant packages for mixed temperature and continuous hot water service. The numeric codes that seemed like simple product designations actually represented sophisticated chemistry that governed material performance under different operating conditions. McKenna recognized that the PEX approach to plumbing represented a fundamental philosophical shift from his copper methodology. Where copper systems relied on protective films that formed naturally under proper operating conditions, polymer systems depended on chemical additives that prevented degradation but consumed themselves in the process. The long-term performance of PEX installations would ultimately depend on whether actual service conditions remained within the chemical and thermal limits that laboratory testing had established. The maintenance inspection that Building Superintendent James Morrison conducted in 2025 revealed the ultimate vindication of McKenna's copper methodology, though McKenna himself had passed away decades earlier. Morrison descended into the Michigan Avenue building's basement mechanical room with digital pressure gauges and infrared thermometers, preparing to document the condition of plumbing systems that had operated continuously for 115 years. The Type K copper risers that McKenna had specified in 1910 showed surface oxidation and minor discoloration, but retained structural integrity that exceeded many modern installations half their age. Morrison's pressure testing confirmed that the heavy-gauge copper still delivered 48 pounds per square inch to upper floors with minimal pressure loss, despite more than a century of thermal cycling and chemical exposure. The 65 thousandths wall thickness that had seemed wastefully expensive in McKenna's era now appeared prophetic, providing copper mass that had absorbed decades of gradual corrosion without compromising system performance. The protective oxide films that McKenna had cultivated through velocity control remained intact along most of the distribution network, creating dark patina coatings that actually enhanced corrosion resistance compared to bright new copper. Morrison's inspection revealed that sections operating under McKenna's 5-foot-per-second velocity limits showed uniform film development, while areas where later modifications had increased flow rates displayed the characteristic gouging patterns that indicated film breakdown and active corrosion. Morrison's documentation included photographic evidence of joint integrity that testified to McKenna's soldering craftsmanship. Lead-tin solder connections showed no signs of the galvanic corrosion that plagued modern installations using dissimilar metals. The flux residue removal that McKenna had insisted upon prevented the localized attack that Morrison routinely discovered in contemporary copper systems, where installation shortcuts had left chemical contaminants embedded in joint areas. The recirculation pumps that had operated for over a century required periodic rebuilding, but the copper distribution network they served remained fundamentally sound. Morrison calculated that McKenna's original installation had delivered hot water to building tenants through approximately 40,000 operating cycles without a single catastrophic failure in the primary distribution piping. The maintenance logs that successive building superintendents had maintained showed routine valve replacements and pump overhauls, but no emergency repairs stemming from pipe wall failures. 3 blocks away, the Palmolive building that had competed with McKenna's methodology told a different story entirely. Morrison's consulting work on that property revealed extensive renovation projects that had replaced the original thin-wall copper installation twice since 1925. The Type M copper that had promised cost savings had failed through erosion corrosion by 1930, requiring complete replacement with heavier gauge material. A second renovation in 1965 had updated the system again, but with specifications that still fell short of McKenna's conservative approach to wall thickness and velocity control. The PEX installations that Morrison encountered throughout Chicago's building stock demonstrated the complex relationship between material chemistry and long-term performance that McKenna had anticipated decades earlier. Buildings constructed during the 1990s with first-generation PEX systems showed failures that correlated precisely with the antioxidant depletion mechanisms that laboratory testing had predicted. Hot water recirculation loops operating at temperatures above 140 degrees Fahrenheit, with chlorine residuals exceeding 2 parts per million, had consumed their chemical protection within 15 to 20 years. Morrison's failure analysis of contemporary PEX installations revealed brittleness patterns that advanced from molecular chain scission through complete antioxidant consumption toward catastrophic rupture under normal operating pressure. The flexible material that had simplified installation procedures became rigid and crack-prone as cross-linked polymer chains degraded under thermal and chemical stress. Unlike copper corrosion, which proceeded gradually and often remained contained to localized areas, PEX failures typically occurred as sudden ruptures that flooded building spaces without warning. The chlorine resistance categories that modern PEX manufacturers encoded into their material specifications reflected lessons learned from early installation failures, but Morrison's field observation suggested that real-world operating conditions often exceeded laboratory test parameters. Municipal water systems maintaining chlorine residuals at the 4 mg per liter legal maximum created chemical environments more aggressive than the ASTM F20023 test conditions that established material ratings. Morrison's comparative analysis of installation costs versus life cycle performance revealed economic patterns that validated McKenna's investment philosophy. The Type K copper system that had cost approximately 15% more than thin-wall alternatives in 1910 had delivered over a century of reliable service with maintenance expenses limited to pump rebuilds and valve replacements. The total cost of ownership calculations that Morrison prepared for building management showed that McKenna's initial premium had been recovered within 12 years, with subsequent decades providing substantial economic advantages. Contemporary PEX installations that promised lower material costs and simplified installation procedures showed different economic profiles entirely. Morrison's data indicated that properly specified PEX systems operating within their chemical and thermal limits could deliver 20 to 25 years of reliable service. But failures that occurred through antioxidant depletion or improper application often required complete system replacement rather than localized repairs. The ultraviolet exposure limitations that PEX manufacturers specified became critical factors in installation quality and long-term performance. Morrison documented failure patterns in systems where construction schedules had left polymer tubing exposed to direct sunlight for periods exceeding the 30-day or 90-day limits encoded in material designations. The photochemical degradation that UV radiation initiated continued long after installation, reducing antioxidant effectiveness and accelerating thermal aging under operating conditions. Morrison's inspection protocols included soil contamination assessments that revealed another advantage of metallic plumbing systems that McKenna's era had never considered. Buildings located near former gas stations or industrial sites showed documented cases of hydrocarbon permeation through polymer piping that contaminated potable water supplies. The copper systems that McKenna had installed showed no evidence of similar contamination, with metal barriers that prevented chemical migration from surrounding soil into the water distribution network. The velocity measurement equipment that Morrison used to evaluate system performance confirmed that McKenna's flow limits remained valid despite more than a century of technological advancement. Infrared flow meters and ultrasonic measurement devices showed that distribution networks operating under McKenna's 5 foot per second hot water limits maintained stable protective films and uniform temperature delivery, while systems exceeding those velocities displayed the turbulence patterns and erosion signatures that led to premature failure. Morrison's final report documented a truth that McKenna had understood intuitively but could never have proven during his lifetime. American building systems achieved century-long durability not through technological complexity or expensive materials, but through systematic application of fundamental principles that recognize the chemical and physical forces acting on plumbing networks over decades of operation. The thick copper walls, controlled velocities, and meticulous installation procedures that had seemed wastefully conservative in 1910 represented engineering wisdom that subsequent generations would rediscover through expensive experience with premature failures. The basement mechanical room where Morrison completed his inspection remained a testament to American craftsmanship that had trusted mass, chemistry, and discipline over marketing promises and initial cost savings. McKenna's copper risers continued delivering clean water to Chicago tenants, their protective oxide films intact, their heavy-gauge walls still resisting the corrosive forces that had claimed thinner alternatives decades earlier.